I know all these things. Okay, so let's go ahead and start today. So we're going to talk about two new gates to start with. The gates we talked about thus far, aren't all the common gates that are used. There's two other gates that are fairly common. One's called an exclusive OR. The other one's called an exclusive NOR. So we're going to talk about these two gates. And then we're going to talk about binary addition, both single bit and multi-bit. And by the end of the lecture and also the activity, you'll be able to do some of lab 2, okay, like the first part of lab 2. And then once you know what structural modeling is, which is the topic for Tuesday of next week, then you'll be able to, finish lab 2. Okay? Lab 2, you're designing a 4-bit adding circuit. Okay? But like I said, we're going to start with these new gates here. And the first gate is called the exclusive OR. It has this logic symbol. So if you compare this logic symbol to the OR gate logic symbol, they look a lot alike. The only difference is the exclusive OR has this additional curve on the input, kind of like a spoiler, kind of like your racy kind of logic gate, like a Lamborghini kind of gate. But that's the difference in the symbol. It's just that added curve on the input side. And then the truth table for an exclusive OR is unlike any other truth table that you've seen thus far, and that's why it's its own separate gate. An exclusive OR, you only get a 1 out when the inputs are different. Okay, so you only get a 1 out if A and B are different value. If A and B are the same value, you get a 0 out. And the SOP equation for F would just be not A, not B, or excuse me, let's bring not A. SOP for F would be not A, B, or A, not B. Right? Because we just write the inputs for when the output is 1 when we're doing SOP for F, right? Now, there's also shorthand notation for this. Instead of writing this SOP like I just did here, you can also use shorthand. Okay, which is this here. See the plus with the circle around it? That means exclusive OR. Okay, so this is shorthand for this SOP. Okay, and in System Verilog, the exclusive OR, because you can't do a plus with a circle on the keyboard. But in System Verilog, you would use the caret. Okay, so when you look at your keyboard, it's the symbol above the 6, so you do a shift 6. Okay, so any questions about the exclusive OR? Okay, so what do you think the difference between an exclusive OR and exclusive NOR is? Yeah, the output's inverted, right? Because it's just like OR and NOR, right? A NOR is an OR with an inverted output. Well, an exclusive NOR is the same as an exclusive OR with an inverter on the output. Okay, so the truth table for the exclusive NOR is just the opposite of the exclusive OR, that you'll get a 1 out of an exclusive NOR when the inputs are the same, and you get a 0 out with it. Okay, and the SOP for F would just be not A, not C, or AB. And shorthand, it would look like this. A exclusive OR would be the whole thing not A. So any questions on that? And see, now this isn't testable, this word I'm gonna put on the board here, compound. But just because you might hear this at some point, you know, these gates are called compound gates. And what's meant by compound in this context is that exclusive ORs and exclusive NORs, you make them out of the other gates we talked about. You know, like each one of these gates can be made out of like ands and ors and nots. I mean, if you were to Google one of these, I'm sure you would find a logic circuit made of those other gates that we've already talked about that would act like an exclusive OR, act like an exclusive NOR. Okay, so you know those gates we talked about prior to today, you know, like the and the or, the and, the nor, and the inverter, you know, the not gates. Those are kind of referred to as basic gates, and you use those gates to make other gates and other devices. Starting next week, a week from today, we'll start looking at common logic devices. Okay. All right. So if there's no questions on this, then the next thing that I want to show you is an example using this K-map. Okay, you're going to see that this is going to tie into what we already talked about. So first of all, here's a review question for you. When you're grouping in a K-map, can you make diagonal groups? What's the only kind of shape group you can make? Right, square, rectangle. So, you know, I can't group these ones or I can't group these zeros back. I can't do that. It's not allowed. So if I were to write an SOP equation for F here, I would just be stuck with single groups here, single groups of one. I have four groups, just a single one. Because I can't group the one with anything else, with any other ones. So my SOP equation that I would get from this is, you know, this cell would just give me not A, not B, not C. And this cell would give me not A, B, C. And this cell would give me A, not B, C. And then here I would just get A, B, not C. Right, because I'm just writing the binary as a Boolean term, right? 0, they're all knotted. 3, this one's knotted. These aren't, that was, you represent the 3 binary sum. Okay. Well, remember the handout that I had on the tables? There was a couple of classes ago. In fact, there's some extra ones on that table by the window if you want a hard copy. But it had all the different laws and identities. I had the Morgans and a bunch of others. Well, if you were to look on that sheet, you would see that just like in base 10, you can factor out a common, you know, variable. So I could factor out the not A from both of these terms, and I could write it like this. And likewise, I can factor out the A from these two terms. And I would end up with this expression here. Well, look inside the parentheses. What's this? That's an exclusive NOR. And what's this? That's an exclusive OR. So I could do this. Okay, I could write it like that, where I'm using the shorthand for exclusive NOR and I'm using the shorthand for exclusive OR. And then could we go further? Could I reduce this further? Could I make this smaller? Less to right. Yeah, not A, then not this B exclusive OR with C, and then you have that word with this A. Ended with this B exclusive OR with C.
This is not another exclusive NOR.
Exactly, right. But sometimes it's hard to see for some people, but what might help is if we use a dummy variable. You know about dummy variables in math, right? You just use like a variable just as like a temporary type of placeholder, if you will. See, if I did this, it might be clear to, if I set X equal to B exclusive OR C, and then just rewrite this in terms of A and X, I would have mod A, then I put in mod X here. And I would put X here. So you see now, for some people anyway, this helps because they can more clearly see that this is now an exclusive NOR function between A and X. Right? So then I can write and then just substitute in for X. Okay, now, like I said, this helps some people. I mean, some people can see it right away. They don't need the dummy variable, but sometimes the dummy variable helps. And then also I got this question in my last section, and some of you may be thinking the same thing. You know, do you need the parentheses here? And the answer is, I'm pretty sure you don't, because exclusive OR doesn't matter what order, just like when you and together or together, it doesn't matter the order. Same way with exclusive OR, it doesn't matter. So you can put the parentheses there and it'll still work, but you don't need the parentheses. Okay? So the reason why, you know, I talk about exclusive OR and exclusive NOR today, and the reason why I show you this example is because you're gonna need these for lab 2. Okay, you're gonna see for lab 2, part of the activity today is a K-map that's gonna look similar to this. See, the key feature here, and when this situation comes up, is when you have single groups that are diagonal from each other. Okay, so you're gonna have a K-map for lab 2, where you're gonna have ones and zeros again that are diagonal from each other. Now again, it's gonna be a little different than this one, but it's the same approach. And you should be able to reduce it down to something like this. Okay. All right, so I got to move the camera. Any questions as I move the camera? Because we're going to talk about binary addition next. All right. Focus. Okay, so where we're going to start with is bit addition, where we're just adding single bits. So 0 plus 0, 0. 0 plus 1. 1 plus 0. How about 1 plus 1? And how do you write 2 in binary? 1, 0. The next time you talk to your parents, you can tell them that in your freshman level college class, you learned what 0 plus 0, 0 plus 1, 1 plus 0, and 1 plus 1 is equal to. You'll be so proud. Taking all that money for you to learn that. Okay, but what we're going to do next is we're going to take these rules. Okay, these are rules of single bit binary addition, and we're going to put them into a truth table. And the reason why we want to do this is because, as I mentioned in previous classes, and as you've seen, you know, I think it was the second class of the quarter. If you have a truth table, from that truth table, you can get Boolean expressions, and from Boolean expressions, you can get a logic circuit, right? So if you want the logic circuit, a logic circuit for anything, put it in a truth table, okay? So to put these rules into a truth table, I'm going to label the top row bit A. I'm going to label the second row bit B. In the result, I'm going to label this bit that's furthest to the right, which is called the least significant bit. Remember we talked about that, LSB, least significant bit. I'm going to label that S. And then the bit to the left of the least significant bit of the result, I'm going to label that C. Okay, now I realize I don't have to do this, but just to be explicit, I'm going to put the zeros here, even though we understand where they're not written. But again, just to be explicit. That. Okay, so I'm just labeling what we're adding together, and what we're adding together we consider inputs, and then also labeling the result that we consider outputs. Okay, I'm going to put this into a truth table. So like we talked about before, in a truth table convention is you put inputs on the left, outputs on the right. Okay, now I'm just going to put these rules into the truth table. So when both A and B are 0, both outputs are 0. We have 0, 1. We got 0, 1 as an output. We have 1, 0. We also have 0, 1 in the output. We have 1, 1. We have 1, 0. Okay. And from this truth table, we can now get the SOP for C, and we can get the SOP for S. Now, this is part of the activity. Okay, so I don't want to give the answer away. But when you have a 4-row truth table like this, you don't need a K-map. Now, you can do a K-map. There's such a thing as a 4-cell K-map, and in my solution for the activity that's posted on the wall there, I show you what a 4-cell K-map looks like, just because if I don't show it, someone usually wants to see it eventually, so I just put it up there. But you see, you don't need a K-map if it's only 4 cells, because if you just compare an output to the inputs, you should be able to get what gate it is. Now, don't say what gate it is, but if you compare the C output to our inputs A and B, you should know what gate gives us a 1 out only when all the inputs are 1. And if you just compare the S output, right? Just look at the S output and compare it to the input, you should know what gate only gives you a 1 out when the inputs are different, right? Otherwise it gives you a 0 out. Because we talked about that gate just like 5 minutes ago. Okay, so that's part of the activity, and also part of what you have to do for lab 2 is write the expression for C from this truth table and write the expression for S for this truth table. And you see the circuit, the logic circuit that performs these rules, it's called a half average. Okay. So any questions about anything up to this point? No questions? All right, well, see, single bit addition like this, you know, it's good, you know, but usually to do any meaningful addition, you're adding multiple bits, not just a single bit. Okay, remember, with a single bit, I can only represent 2 values. Okay, remember this expression we talked about, the number of values that you can represent with a certain number of bits, it's just equal to 2 number of bits, right? So you got 1 bit, 2 values, 2 bits, 4 values, 3 bits, 8 values, and so on. So, you know, most useful binary addition, you're going to have more than a single bit. You're going to have multiple bits. Okay, here's an example of adding 2 4-bit binary numbers. Right, so with 4 bits, I have how many possible values? 16, right? 2 to the 4, 16. So with 4 bits, I can represent numbers 0 through 15. Taking this as the least significant bit, right? Taking this as the 1s column, then 2s, 4s, and 8s. What would this binary be in base 10? 0, 1, 1, 0. What's that in base 10? 6. Right? If we take this as 1, we got a 2, we got a 4, we don't have an 8, 4, 1. So this would be 6 in base 10. So that would be 6. More like Eugene. 6. Okay, how about this? 0, 1, 1, 1. 7. So you see, this is the binary addition of 6 and 7. Now, when you add multiple bit binary numbers manually, you do it the same way you would add multi-digit base 10 numbers. Now, you probably haven't done that in a long time, right? Because people just punch into their calculators. But a long time ago, when you were first learning addition manually, right? You learned to go column by column. Right? Same way when you're adding multi-bit binary. You start with the least significant bits and you just go column by column. So here I have 0 plus 1, 1. Then I have 1 plus 1, which is 0, carry the 1. Okay, now when I get to this column here where I'm adding 1 plus 1 plus 1, I'm adding 3 ones. This half adder can't do that. This half adder can't add more than 2 bits. Right? There's only 2 inputs in its truth table. So a half adder would not be able to add 1 plus 1 plus 1. But there's another logic circuit that's called a full adder. And the full adder can add 3 bits because a full adder has 3 inputs. And typically those inputs are labeled A, B, C, I. And it still has 2 outputs. One output is S, and the other output is typically labeled C0 or CO. Can you guess what CI and CO stand for? Carry in, carry out. Yep. See, the half adder only has carry because there is no carry in, so everyone understands that the carry out. But because the full adder has both, that's why we have the subscripts I and O. Okay, so since the truth table for the full adder has 3 inputs, how many rows in this truth table? How many values can you have with 3 bits? 8, right? Again, see, we're always doing this. This has to be like ingrained in your brain, right? Okay, yeah, 8. So they all could be 0, 1. Again, I'm just counting in my head in binary here as I list these. Remember we talked about that? By convention, you put the inputs in binary order. Yep. That's the convention anyway. That's fine. I always double check because it's easy to mess up. 2, 4, 6, 8, 0, 1, 2, 3, 4, 5, 6, 7. Okay. So now to get what the output equals, we're just adding these 3 bits. Well, if you're adding 3 zeros, of course, the result is 0. And then if I'm adding 2 zeros and a single 1, the result is a 1. And that's true for all the rows that just have a single bit equal to 1. Down here. Okay, and then if you're adding 2 ones, that's a binary 2. The output would be 1, 0. So also here we have a binary 2 result, and a binary 2 result here. And then this is the case we were just talking about up here. 3 ones, which is 3, which in binary would be 1, 1. Okay, so everybody see how I did that? So to complete this multi-bit addition here, 1 plus 1 plus 1 would be 1 with a carry of 1, and this would be 1. And then 1, 1, 0, 1 in binary, what is that in base 10? 13, it better be, right? Because 6 plus 7 is 13. All right, we have an 8, we have a 4, don't have a 2, have a 1. 8 plus 4 plus 1, 13. Okay? So, for lab 2, you're not only going to design a half adder, but you're also going to design a full adder. And unlike the half adder, to get the reduced expressions for SOP, CO, and SOP, S, reduced. I mean, these are also reduced, but because the truth table is so small, you'll get the reduced just by looking at the truth table and getting the gate from the truth table like we talked about earlier. But when you have a truth table like this that has 8 rows. Now you got to use an 8-cell K-map. And you're going to have a K-map for each one of these. So you'll have a K-map for C0 and you'll have a K-map for S. Okay, because remember, what goes in the cells of the K-map are the output that goes with the corresponding inputs. Okay. All right, so you'll have to take this truth table, just look at C0, fill out that K-map, take this truth table, just look at S, fill out that K-map, and then use your knowledge of K-maps to get the reduced expressions. Now, one of these, I'm not going to tell you which, you'll find out when you do the activity and also lab 2. But one of the K-maps is going to look like this. Okay, so you're going to get ones that are diagonal from each other. So I'm expecting you to reduce it like I showed you this example. You're going to get something similar to this. Again, it's not going to be the same, but it's going to be similar. Okay. Okay, so any questions up to this? Am I still in view here? I think I gotta move the camera a little bit. All right, so you probably noticed that I didn't put handouts on the tables like I have been for activities, and that's because there's no handout for the activity today, because the activity today is part of the prep work you have to do for lab 2. Okay, and if you go on Canvas and you look at lab 2 assignment part 1, number 1, that's the activity where I want you to draw a black box diagram for the half hour. So what does a black box diagram tell us again? Like, what's the purpose of a black box diagram? We talked about this a couple of times. Yeah, main inputs and outputs. So your half adder is going to have how many inputs? 2. How many outputs? 2. Okay. Then I also want you to do a black box diagram for the full adder. So how many inputs? 3. How many outputs? 2. Okay. That will take you all of 15 seconds to do. Right? Okay. Truth table. Well, I gave you the truth table, so you just got to copy those down. Okay. But then this is where you'll have a little bit of work. You want to get the reduced SOP for the half adder. Again, you can just look at the table, truth table, and get what the gates are. Now, in the activity solution, again, I do show a 4-cell K-map in case you want to take a look at what it looks like. But I'm not expecting you to do a K-map for the half adder. Okay, but then this is a little bit of work. You'll have to do a K-map, like I said, for both the CO carry out and the S outputs of the full. Okay. So that's the activity, and then I just wanted to make a few comments on the first part of lab 2, because lab 2, when you get to Vivado, it's a little bit different than the first 2 labs. Okay, and like I've said previously, make sure you have separate projects for the lab. So right now you should have a project for lab 0, you should have a project for lab 1, create another project for lab 2. Now in lab 0 and lab 1, you had a single design source and you had a single sim file. But in lab 3, you're going to start off with 2 design sources and 2 sim files. You're going to have a design source for your half adder, and you're going to have a separate design source. It's going to be within the same project. Okay, so I'm not talking about a separate project. The full adder and the half adder, they're all within the same project. It's just you got 2 design sources. So you could call it like HA for half adder and FA for full adder. And then you also need 2 sim files. So you'll need a sim file for the half adder, and you'll need a sim file for the full adder. Okay. Now, how many test cases are you going to need to make sure that your half adder is working correctly? 4, right? Because there's 4 rows in the truth table, right? I mean, When you did lab 0 to prove that that logic circuit worked, because there was 8 rows, you had in the truth table, you had to do 8 test cases. Then for the locked box, your truth table for the locked box had 16 rows, so you needed 16 test cases, right? Okay, so you need 4 test cases for your half adder. How many for the full adder? 8, right? Because you want to make sure it's doing this truth table. Okay. And when you have multiple files in your project, when you go to simulate a file, you have to make sure both that design source and that sim file that corresponds to it is the top module. So when you go to simulate your half adder, you got to make sure that that pyramid symbol is next to the design source for the half adder and also the sim file for the half. So you have this when you sim the half adder, and then you have to switch it by you right click. You know how to set top module in there, right? So when you go to simulate your full adder, you'll have to make sure the pyramid symbol is by both of them. I can't tell you how many times I have someone that the simulation's not even what they expect, or it crashes or something, and it's because they got this the top module, but this one not the top module. They have the wrong parent. That can cause problems. So be real careful with that. Okay? All right. So the goal today, or well, not really today, but before Tuesday of next week, if you can get a good simulation for your half adder and you can get a good simulation for your full adder, then you're in really good shape for Tuesday. Because on Tuesday, okay, we're going to learn what structural modeling is. And once you know what structural modeling is, you'll be able to take your full adder and your half adder and make a circuit that can add multiple bits. Because just like how you manually add multiple bits a bit at a time, that's how the hardware does it. See, the hardware has an adder that adds these bits. It has another adder that adds these bits. It has another adder that adds these bits. It has another adder that adds these bits. See, to add 2 4-bit binary numbers, you need a circuit with 4 adders. And the adding circuit that you're going to eventually design next week, once you know what structural modeling is, it has 3 full adders and 1 half adder. Can you guess why it's 3 full adders and 1 half adder, and why it's not like 2 half adders and 2 full adders? Yeah. For this least significant bit column, I don't need a full adder, right? I'll never get a carry in. So you see, we'll use a half adder for this column, but for all the other columns, we're going to need a full adder. Okay. So, structural modeling is how in Verilog you take multiple modules, for example, 1 half adder and 3 full adders, and how you connect them together. Okay, so today you'll have 2 design sources, 2 sim files. On Tuesday, you'll add a 3rd design source and a 3rd sim file, where the design source connects everything together, and then the sim file tests the 4-bit, the final result, which is a 4-bit adder. Okay? All right. Do you have any questions? Because at this point, you should be able to do the activities, and just like all the activities, everybody work together and just pass one in from the table. Now, whatever one you pass in, I would make sure that person takes a picture of it, because you're going to need it for lab 2. But like I said, there is no handout. So just use a piece of paper. If you don't have paper, there's paper in the printer that you can use. Also, there's scrap paper on that table. You can use the back. You need a piece of paper. And then once you're done with that, now again, remember, I can't stress this enough, because this happened this morning in my earlier section. If you're going to leave for the lab portion, make sure you don't leave before your group passes in the activity. What I would do if I was a person at the table that was going to leave after the activity is done, I would make sure, like I would be the person that would hand it to you. Okay, I had a couple people in my earlier section today. They left before I got the activity from their group. So I don't know if they were here for the whole group. And if I don't know, I don't give them credit. Okay. Okay, so don't leave until your group has passed in the activity. You're gonna leave. Okay. All right, so with that, any questions? Okay, well, if questions come up, please ask.